Start recording. So it's a pleasure to have Irene Valenzuela today with us. She's from Harvard University, and she'll be talking about Chern-Weil global symmetries and how quantum gravity avoids them. So take it away, Irene.
Okay, thank you very much for the introduction, and thank you so much for the invitation. It's the first time I'm giving a seminar here, so I'm happy to meet you all. And I hope you will enjoy the seminar. So my plan is to talk a bit about Chern-Weil global symmetries, which is based on this recent paper with Heidenreich, McNamara, Montedo, Ruiz, and Rudelius. And please, like, if you have any question, I'm very happy if you just interrupt me at any time. Also, I guess there is some, we can have different backgrounds, so I will try to go slowly, but please, like, if you have any question, doesn't matter how basic or complicated is the question, just ask and interrupt me, and I can make sure that we are all on the same page. Okay. So symmetries, I guess all of you agree with me that they have played a very important role in physics to describe nature and progress in high energy physics. Recently, actually, even if this is like a very old topic, there has been a revival on how to think of global symmetries and how to generalize the notion that we had to incorporate like more like new types of global symmetries that can help us to reformulate old phenomena in this more modern unifying language that we are starting to use. So in this work, we want to draw the attention to a large type of generalized global symmetries, which we call Chern-Weil global symmetries. So I will explain in detail what these symmetries are, and I will review a bit what are the generalized global symmetries. But before, let me just mention that the whole point is that we believe that in quantum gravity, global symmetries are actually not allowed, in the sense that they should be broken at some high energy scale, or they should be gates. And how specifically these symmetries get broken or gates give rise to a lot of interesting physics that I will discuss. So what we do in this work is to understand how this large class of global symmetries can actually be broken or gates, and what does it mean. Okay, so let me already say, although I will describe this in more detail, that this belief is a Swampland conjecture. So it's a constraint that any effective field theory should satisfy to be consistent with quantum gravity. And I will explain in more detail why we believe that this is true. But I will not assume that the conjecture is true. So I'm not going to assume that the conjecture is true. I'm just going to study what the symmetries are and to study how we can break them or gauge them, and how, in fact, this phenomena is something that occurs in string theory. So like all these mechanisms that I will describe using the language of QFT are useful to understand, why many top-down aspects that we find in string theory, they are not just a matter of looking under the lamppost, but they are there because they are needed to break these symmetries, which hints that maybe all these phenomena that we get from a top-down perspective could be more general than string theory. Okay, so the outline of the talk is first, I will review why it's believed that there are no global symmetries in quantum gravity. And then I will review what is this notion of generalized global symmetries, how to work with them, and define this new large class of Chern-Weil global symmetries. Then I will explain how to break them and gauge them using examples, because I think sometimes it's easier to understand things having a concrete example than just abstract and some abstract formalism. So I will focus on two examples that are very representative, and I will explain how a lot of old physics, like for example, the Toff-Polyakov monopole with work-volume degrees of freedom, and things like this can be understood by requiring that these Chern-Weil global symmetries are breaking in a consistent way. And then typically, actually, then the next thing I do is to talk about the realization in string theory, how these things are broken there, and how we can really derive aspects of string theory just from the absence of global symmetries. But since I think this audience is more phenomenological, I will first give some remarks about the phenomenological implication, and at the end of the talk, I will go to the string theory part. Okay, so let me start. So the Swamplan, so we say that, there is a Swamplan conjecture that forbids this presence of global symmetries, and Swamplan is a word that we use to define those effective field theories that seem apparently consistent, so they are anomaly free from an IR perspective, but actually they cannot be embedded in quantum gravity. So the idea is that if you consider all the space of EFTs, that of effective field theories that you could construct at a given energy scale, even if you follow the rules of quantum field theory, not all of them will remain consistent once we couple the effective field theory to quantum gravity. So the ones that are not consistent are said to belong to the Swamplan, while the ones that are consistent and can, for example, arise from string theory belong to the landscape. And the Swamplan constraints distinguish the theories that live in the landscape from the theories that live on the Swamplan. But the message is just that, not, as I put here, not everything is possible. So there are new constraints that have to be satisfied to guarantee a UV completion in quantum gravity. And this is a very ambitious program because we are trying to understand the quantum gravity principles, but I think it's also very rewarding because if indeed we can prove that there are some additional constraints, this can give rise, this can have very interesting phenomenological applications because they can be used as new guiding principles to progress in high energy physics, new constraints, and even if I will not discuss in this talk, they can also provide new insights on the naturalness issues of our universe. So in the past few years, there has been a lot of activity in this program. So there are different conjectures that have been proposed that provide Swamplan constraints that an effective field theory has to satisfy. And one of the things that we are discovering is that they are actually related. So it could be that in the future, instead of having many different conjectures, they all reduce to a few quantum gravity principles that we are starting to discover. But at the moment, this is sort of the map of conjectures that we have. And in this talk, I'm just going to focus on one of them, which is the absence of global symmetry. So this is the oldest and most widely accepted one, from which many of the others can be derived.
So could I ask a question here?
Yes,
Sorry.
please.
When you talk about this Swamplan and the quantum gravity, are you assuming string theory as the quantum gravity, or you're just being generic about the quantum gravity? For instance, let's say that it was loop quantum gravity. Would these conjectures still apply there, or are you putting loop quantum gravity also in the swamp?
Yeah, so that's a good question. And it's a question that you have to try to answer if you work on a Swamplan program. So in principle, these conjectures are supposed to be general. Sometimes they are also based on black hole arguments that one would expect that are more general than, regardless of whether you talk about string theory or not. So they are supposed to be general. They are not proven to be general. In that sense, they should apply to any quantum gravity consistent description that you could have. Now, in practice, the most rigorous proofs of the conjecture come from string theory. So it's under debate whether, it's an open question, whether in the end we will be able to prove that they are more general, or whether even if we believe they are, actually we can only prove them in string theory, so they can distinguish string theory from other quantum gravity theories. Yeah, it's like there is no definite answer there.
I see. Okay, thanks.
Let me say, there's also some, especially the past few years, there is some proposal also that it could be that somehow everything is connected to string theory. This is called string universality. That doesn't mean that there are no other options, but that somehow there should be a way to connect them, even if we don't know how yet. And in that sense, everything that should be consistent with quantum gravity should arise somehow from string theory. This is what is called string universality. So there are many people working actually on trying to show this, and it's possible to show this for highly supersymmetric cases. Like for highly supersymmetric cases, people are showing that anything that is anomaly free and consistent actually arises from string theory. But it's a completely open question when we have little, I mean, we don't have supersymmetry, and we have very little supersymmetry. So we'll see in the future what's the answer.
Okay, thanks.
Excuse me, a related question. Here at the left corner, left bottom corner of your slide, I see that all non-supersymmetric vacua are unstable, okay, because of this conjecture. Now, we live definitely in non-supersymmetric vacua. And if it is unstable, our descendants will never have any contact with any other vacuum, because
this can be metastable. When I put here,
wait a minute. If we live in non-supersymmetric vacuum, it may be metastable, but we will never, we or our descendants will never survive in a huge Big Bang when it starts decaying into the stable vacuum. So our world and the world of all our descendants, to all practical purposes, is either it is this world or anything else is not accessible to us. So if physics have to do with our
so let
me
point out. So here I put unstable, but actually it's allowed metastable. So this is here the point. I will not discuss this conjecture, but the point is that any non-supersymmetric vacuum should eventually decay, but it can be very, very long-lived. So it's completely fine with our universe, because actually by the Higgs potential, we believe that. So that would be fine, yeah.
All other consequences which you list here, they are exactly on the same footing.
Yeah.
Like in our everything, if it's violated by our world, everything else might well be violated in our world by some mechanism, you know. So in a sense, this is a philosophical question which you are going to discuss now. It's not a physical question in the old sense of this word, because old physics deals with only with the things which we can measure, observe, or detect.
Okay, in any case, I will not discuss this conjecture in this talk, so maybe we should stop it. But there are many things to study there. And anyway, I have like studying bubbles of nothing. I think eventually we will be able to prove that you need supersymmetry to have a completely stable vacuum. But you can ask me about this later after the talk in the questions.
Okay.
Okay, so yeah, so the only conjecture I'm going to discuss now is the absence of global symmetries. Okay, this is like the oldest and most accepted conjecture. It says that any global symmetry should be broken or gates in quantum gravity. In the sense, when I say gates, it means that it's associated to some gates degrees of freedom, okay, or broken. Now, the motivation originally came from black hole physics, because if you have some global symmetry, since Hawking evaporation is blind to the global symmetry, you could end up with an infinite number of remnants for all the possible representation of the global symmetry group, which are the generating mass, and that would give rise to an infinite entropy and would violate entropy bounds. This is just a motivation, okay, it's not a proof. And why this conjecture is so important is because of all the evidence that we have gathered in the past years. So, for example, I mean, it's very well known that already in perturbative string theory, this is proven that there are no global symmetries. It has most recently been proven in the context of holography or of ADS-CFT with splittable symmetries. And last year, there is also a lot of activity trying to give more topological arguments of why global symmetries should always be broken. Now, as I said, I'm not going to assume that the conjecture is true, but rather the opposite. Like, I'm going to give evidence for that. Like, we are going to study this class of global symmetries. Especially at the end of the talk, I will show you that indeed they are always broken or gates, and how they get broken or gates is very interesting because these are responsible of many phenomena that we observe in quantum field theory and string theory. So I just want to reformulate all these phenomena as coming from the absence of these global symmetries that I will explain to you. Okay, so let me review what is a global symmetry and what are these generalized global symmetries that are playing such an important role in the recent years. Okay, so global symmetries, we are all used to them, right? Like we learn from the very beginning in physics that sometimes we have some transformation that commutes with the Hamiltonian and acts on the Hilbert space of physical states. Since we are going to get mixed with quantum gravity, it's better to reformulate this notion in terms of some operator. So the point is that global symmetries are characterized by some unitary local operator, which is topological. Okay, so the notion of topological is what replaces just the notion that commutes with the stress energy tensor with the Hamiltonian. And this symmetry must act on the Hilbert space, which means that there should be some local charge operator, which is gauge invariant, and that is charged, okay, under this symmetry. So it should not commute with the symmetry operator. Okay, when we talk about U1 global symmetries, then we can define a current which is conserved, okay? So if we are in d-dimensional space-time, this global symmetry is going to be associated to some d-1 form current, which is closed, okay? This is the conservation of the current. And we are going to have a conserved charge, which is the integral of the current. And in terms of this charge is how we define this symmetry operator that is topological. And then we have, as I said, some charge operator that creates some zero-dimensional dynamical charge state, like some particles. So we need to have particles that are charged under the symmetry in order to be able to talk of a symmetry to start with. Okay, so this is an ordinary global symmetry. Now, the point is that we can generalize this notion to higher form global symmetries in which these charge operators are not localized at a point, but they are localized on some higher dimensional manifold. So these generalized global symmetries that were defined in this seminal paper by Scheiber et al., they are P-form or global symmetries, such that the charge operators are supported on p-dimensional manifolds, okay? And then the thing is that I will have a d minus p minus 1 form current. Sometimes it's a bit difficult all this to keep track of all these forms, but I mean, don't worry too much about it. The thing that you just have a higher form symmetry, and then you have some conserved charge, which is defined in terms of this higher form symmetry, and then some topological operator. Okay, in the same way. And then the states that are charged under the symmetry are not particles, but are higher dimensional objects. Okay, so a P-form global symmetry will have some P-brane that is charged. So if P is equals 1, I will have a string, or P equals 2, I will have a membrane, and so on and so forth. Okay, this is the generalization. Okay, so maybe to make it more concrete, let me explain it with an example. Okay, so there is this canonical example of a gauge field theory. Okay, so we can be all more familiar about it. So if we have a one-form gauge field, okay, so when I hope people are used to this notion of P-form of differential notation. Otherwise, ask me, okay, you can ask. But like if we just have some gauge field theory and we have a one-form gauge field and we have a two-form field strength, then in addition to the usual gauge symmetry that we are used to, we also have a one-form global symmetry because the theory is invariant under this shift of the gauge field, okay, where lambda is a one form, it's a continuous one form, okay. So this is a global symmetry of the theory. And since it's a shift of a one form gauge field, it corresponds to a one form gauge global symmetry. Now the current is just the field strength, okay. So in the absence of charge states, this current is conserved, right? Because by the equation of motion, the derivative of the Hochstadt of F2 is 0. So we have this global symmetry, and we can define these symmetry operators and these charge states. So the Wilson lines are the charge operators under the symmetry. And the symmetry gets broken in the moment in which we add some charged particles, because then the conservation of this current is going to be different from 0. Okay, any question about this? Okay, just to go slowly. Now, in addition to this electric one-form symmetry, we also have a magnetic symmetry of the dual gauge field. And in this space-time dimension, it's going to be a D-3 form global symmetry. If we are in 4 dimensions, then it's also a one-form global symmetry associated to the magnetic one-form gauge field. And we have the same game, and now the Toft operators are going to be charged under the symmetry. And the symmetry is going to be broken once we add monopoles, because then the conservation equation of the current, which is just F2, is going to be different from 0.
So then can I ask a question here? So if you didn't add the charged particles, then this symmetry would be preserved because you would add your theory would just contain membranes and no particles. Is that the idea?
Yes. Yeah.
But if you have membranes and particles, then the one-form global symmetry would be broken.
Exactly. So actually, these charge operators, what they create is a string. So these membranes are like one membrane, so it's one-dimensional, so it's a string. So we have these Wilson loops and Toft lines that, if they are dynamical, we have strings that are charged under the global symmetry. But if we don't have particles, what happens is that these strings cannot break. So you just have some strings that cannot break, and then we have a one-form global symmetry, and it's exact. But in the moment in which we add particles, the strings can break because the particles are at the endpoints, and then the global symmetry is broken.
I see. Thanks.
Okay. So yeah, so in general, I mean, we can generalize this for any P-form gauge field. So we have these transformations, right? That if the theory is invariant under them, we'll have a P-form global symmetry with a current that is given by the field strength. Okay. And we'll have the electric and the magnetic one. So we'll have a current with the Hochstadt and without the Hochstadt. Now, I told you that global symmetry should be broken in quantum gravity, and that also applies to this type of global symmetries. So there are two options, okay? We can gauge the symmetry, okay? Which means that we can couple the gauge field to some P+1 form field via some Stuckelberg coupling. So we couple the current that we have to some additional dynamical gauge field, so that we can write this coupling in a maybe more familiar way as a Stuckelberg coupling, no? So that our P+1 form field gets massive by eating up the original P4 symmetry, which means that the theory is only invariant under the combined transformation, right, of this global symmetry and the gauge symmetry of the B field. So what we are doing is to promote this global transformation to a local transformation of the B field, and that's why the symmetry gets gauged. So if we think that P is 0, I mean, so this would be a usual ordinary symmetry, a zero-form global symmetry, this is the typical Stuckelberg coupling, right? Like we have some gauge field that eats some axion, and then the zero-form global symmetry of the axion gets local and gets gauge, right? Yeah, so in this case, this is fine for quantum gravity because the charge operators that you can construct under this global symmetry are actually no longer gauge invariant. So there is no global symmetry. I mean, this is completely fine. Any questions?
Can I ask a question here? So often when we gauge a global symmetry, we find new global symmetries as a bonus. For example, right?
Yes, but
yes, go ahead.
So for example, here,
work? Yeah.
like you could say, okay, here I'm gauging this global symmetry of A, but I'm doing this by introducing this B field that has also some global symmetries. Maybe that's what you have in mind.
Precisely.
But,
yes.
but the point is that this is fine because it's gauge as well. So the thing is that this, well, I will explain. So, no, sorry. So the point is that this coupling is not only gauging the P-form global symmetry of A, but it's actually breaking the P+1 global symmetry of B, because this is like a spontaneous breaking of the field. So I will explain in the next slide, but even if we are adding more symmetry, they are not exact. They are broken. Like maybe let me already, yeah, look, I can already explain it here. Yeah, like this is the equation of motion for the B field, okay? H is the field strength. So this equation of motion is telling me two things. It's telling me first that the current, the original current that I have for A is exact, which means it's consistent with the fact that the symmetry is gauge. But it's also telling me that the P+1 form global symmetry associated to the B field is broken, because this is exactly the conservation equation of that current. So the current would be the Hodge dual of H, and then this is different from 0. So one is gauge and the other one is broken. So the same coupling is giving you the two things at once. So there is no symmetry left. Yeah.
Isn't there also, though, a magnetic symmetry for this P+1 form? So
yes.
like a D minus B minus 2.
That's what I was asking about. Yes, that's what I was
from the Bianchi identity.
Yes, but then, so we can dualize this to the dual fields. So the B field, like for example, okay, I will do it later in more detail, but let me say it briefly. Like when you dualize it, then the things get exchanged. Like the magnetic symmetry of the B field will be gauge, and the magnetic symmetry of the A field will be broken. So like the story is the same, but exchanged. But let me, in a couple of slides, I will do this in detail in 4 dimensions. So we just have then a B field and an axion, and then I can show you explicitly the equation of motion and everything, how to see that there is no symmetry left. Okay.
Thank you.
Any other question? Okay, so typically to gauge it, we have to add new fields, okay? But then I will show you that everything, nothing is exact, like all the symmetries are broken of gauge. The other option is not to introduce any new field, but to break it by having charge states, as we said before with the one form gauge field. So if we add some charge P branes, in this case, like for example, for a 1-4 global symmetry, we just add electrons. Then because of the equation of motion, right, the conservation, the current is no longer going to be conserved, and then the symmetry is also broken. Okay. So this tell us that actually absence of P-form global symmetries is associated to completeness of the spectrum. That whenever we have some complete spectrum, in the sense that we have charged states, then we are going to get rid of these symmetries, and vice versa. Because actually, if the spectrum, like if we have some global symmetries, because the spectrum is not complete. I say complete because if we only add some states for some charges and not all of them, then the global symmetry, the U1 global symmetry is not broken completely, but broken to a discrete remnant So that's why usually one has to include a complete spectrum. Okay, and this is, we already discussed this next to the question. So the other way to break the symmetries is already by the coupling that we had before. No, when we had these couplings that are gauging one of the symmetries, is also breaking the other one. So we can break symmetries either by adding charge states or by adding all these BF Chern-Simons couplings. Okay. Okay. Yeah, and just a last comment. This is why actually in a previous paper we proposed that one need to have these sort of Chern-Simons and BF couplings always in order to avoid these symmetries. But I mean, this is something that we now study in more detail. Okay. Any other question before I go to the Chern-Weil symmetries?
Yeah, so this Chern-Simons coupling that you're saying, so that means that you always have, this is in D dimensions. So like in 5 dimensions, the Chern-Simons can always just be added.
Yes.
But do you think of it as integrating out some fermions? Where does this Chern-Simons coupling come from?
So the thing is that, okay, with Chern-Simon here, I'm thinking of a broad definition of Chern-Simon, in the sense that it's not just the usual Chern-Simon with the gauge field, but like any, like BF or like any coupling of different gauge fields, I call it sort of Chern-Simon. Like when I have also an axion and then a gauge field and another gauge field, like phi FF or phi FHF, things like this, like a broad sense of Chern-Simons in which we have just some triple coupling, including 3 types of gauge fields. And the thing is that, yeah, like what we realize is that, so one typical feature of string theory is that you always have this type of couplings. Like you never have some gauge field alone, like it's always coupled to something else, either an axion or some other gauge field or something like that. And you could think that it's just a matter of the string compactifications that we study. But I think it's deeper than that, and it's related to the fact that all these couplings are helping you to avoid all these global symmetries. So you could try to promote it to a general statement and not just a matter of the lamppost. But at the moment, I mean, the truth is that, so I will explain it. So this is more clear with the Chern-Weil symmetries, but at the moment, it seems that there are the 2 ways. Either you have these couplings, like the gauge field is coupled to something else, and therefore the symmetries are broken, or you have charge states. And they seem to be 2 different things that you could get rid of the symmetries either way, but actually they are correlated. And I think that's why we observe both things in string theory. And how they are correlated, in order to explain that, I need to go to the Chern-Weil symmetries.
Yeah, I mean, I guess I was just saying that if you have an axion coupling to FF dual in 4 dimensions, it's a higher dimension term. So you typically think of it as coming from integrating out some fermions. And so all I was just wondering is if there's a connection between the Chern-Simons couplings and the completeness of a spectrum, you see.
Okay, I see. Sorry. Yeah, you're wondering like whether, maybe in the low energy theory you observe the Chern-Simons, but you can understand it from completeness of the spectrum of a higher
because you
dimensional
have to
theory.
integrate out charged fermions, you see.
Yes. No, yes, you are completely right. Sometimes you can understand it that way.
That's all. Yeah, sorry. It was
Yeah.
minor point. Sorry. Yeah. Okay.
No. It's a nice point. It's true. They get correlated when you change the dimension. That's completely true. Okay. Yeah, the correlation I will talk about is without changing the direction. So that's why it's a bit different. Yeah, that I mentioned. Okay. So these are typical generalized global symmetries. So what we do now is we want to draw the attention to more general symmetry. So in the same way that we can have these currents, which are just the field strength of some gauge field, and we have these P4 global symmetries, we can think of more general situations in which we have products of the gauge field strength. Okay, so we use the name Chern-Weil global symmetry for any global symmetry whose current can be written as some product of some gauge field strength. Okay, with any, even abelian, non-abelian, like different degree of the forms, and also including axions or things like that. And why it's useful to have a unifying language for these symmetries is because actually they are not easy to break, in the sense that the Bianchi identities of the gauge fields guarantee conservation of all these products of the currents. And if the gauge groups are compact, they are always going to correspond to U1 global symmetries. So as I said, like, they are not easy to break because of these Bianchi identities, unless we add like new charge states or things like that. And that's why breaking the symmetries constrains the dynamics of the theory. So the point is that using this unifying language, we can understand, for example, the existence of actions and Chern-Simons terms. And I will show you all these things, like the existence of actions, localized degrees of freedom in monopole work volumes, brain dissolving in brains and then in brains. All these phenomena, we can reformulate them as consequences of gauging or breaking these Chern-Weil global symmetries.
So for instance, if I look at the F wedge F current, this corresponds to adding in some higher membranes into, just say some non-abelian theory in 4 dimensions. That's what it would mean.
Yes. The thing is that in 4 dimensions, this is a 4-form current, which means that it's going to be associated to a -1 form global symmetry.
Yeah.
So the membranes that you are adding are like -2 membranes, which seems very exotic.
Yeah.
But I mean, we discussed in the paper this case, and I think it makes, like, I think there is a way to make sense of it. I mean, it's not like the same way that we make sense of instantons, like that are also not like -1 things. I think there is a way to make sense of these objects. You don't have to think of them as dynamical objects, not that you can measure in an experiment. It's more like some process, like some instanton or things like that. So it's like a step further to that.
Yeah, because this is a 4-form current, right? So
exactly, it's a 4-form current, so it's going to be a -1 for global symmetry. But the point is that, okay, let me say now, because actually I don't have a slide for that. So we have a part on the paper in which we discuss what does it mean to have a -1 for global symmetry. And in a few words, I think the meaning is that -1 for symmetries are associated to having free parameters in the theory. So all this idea, I don't know, maybe you have heard of, that we believe that there are no free parameters in string theory, that everything should be determined dynamically, and so on, can be reformulated as claiming the absence of -1 for global symmetries. So in the same way that a P4 symmetry, the charge is carried by a p-dimensional manifold, p-dimensional object, the idea is that the charge under a -1 for symmetry is carried by the entire space-time.
Oh.
So they are like labels of the theory, like they are parameters of your theory. So different charges correspond to having like different possible values of the parameter, and they label different vacua. And the idea is that if the symmetry is broken, it's because there should be a way to deform the parameter like this. I mean, it should be dynamical. And the way in which it's gauge, I mean, to say that a -1 for symmetry is gauge, is like what we do in axion monodromy, like when you give a potential for an axion, such that you get a multi-branch potential, so that you are preserving the discrete symmetry of the axion, but because the potential has this multi-branch structure, such that, like it preserves the discrete symmetry, but still the axion gets a mass. This is like gauging the symmetry because the axion is eating this parameter. So it's like the Stuckelberg mechanism for the axion, and that's the axion, what is called axion monodromy, that is used in inflation and I don't know, for other beyond standard models.
Yeah, well, it's not exactly a Higgs mechanism, because in Higgs mechanism, the degrees of freedom are changing here. Here, you're not changing the degrees of freedom though, right? When you eat this parameter, I don't know what that means, but
you are not changing, because a parameter doesn't have a dynamical degree of freedom. That's why there are no dynamical fields. but still has some meaning in the sense that different values of the parameter describe different vacua. So it has a physical meaning, but it doesn't have propagating degrees of freedom.
I
That
see.
would be
Okay.
the-
I'll
Anyway,
have to ask you later again. It's okay. Yeah. No.
Can I
see
ask
if
a
it-
question as well?
yes.
So from things you've just said about -1 form symmetries being connected to existence of parameters in a theory,
Mhm.
I'm a little bit confused. For example, n equals 4 super-Young Mills has a 't Hooft coupling, which is a perfectly nice parameter. What's wrong with it? Does it
Well,
fit?
but from the gravity side, right? This is just given by GS, right? By the string coupling.
Now, GS is 1 over n, no?
So I mean, the 't Hooft coupling, you mean GSN, right?
Yeah, yes.
Yeah. So GS is it's a dynamical thing, and N is a flux, right? So
Yeah.
the point is that flux is happening something similar to this axial monodromy. Like this flux is actually gauge. Like the fact that we can have transitions between different values of the fluxes is like if we have this branch, like this multi-branch structure, and we have membranes that nucleate, that change the value of the flux, which means that since they are connected, what is happening is that the symmetry is gauge. So there is no like a free parameter, like there is no global symmetry. It's like when we try to, you have always the two options. You can break it or gauge it. That would correspond to gauge it. And you can understand it that way. Of course, it's a free parameter from the CFT side, but that's the boundary. But from the gravity side,
yeah, but I was asking from the CFT side, right? So in the CFT side, you have a QFT, a well-defined QFT that's by itself. In principle, I don't have to invoke ADS CFT to talk about it. And you can ask, can I couple that CFT to gravity or whatever? Follow your swampland conjecture stuff. But that CFT has two free parameters, lambda and then.
Mm-hmm.
So
I mean, the thing is that, okay, there are two ways. So either we are thinking of the CFT and then we think of the gravity dual, and then the conjecture should apply in the gravity dual, right? Because any gauge symmetry in the gravity dual is a global symmetry in the boundary. So the question is what happens when you have dynamical gravity, not when you have the field theory. Or you try to engineer the CFT as a defect on a gravity side, but then in order to connect gravity, then you lose conformal invariance. So let me say, all these swampland conjectures they always applies to EFTs that are coupled to Einstein gravity, and gravity is dynamical. If gravity is dynamical, they don't apply. Like all these conjectures, when you send the Planck mass to infinity, they disappear. And that's the point. Like you have some gauge symmetry, and maybe you have some global symmetry that is gauge. You send the Planck mass to infinity, and then this gauging disappears, and then you restore a global symmetry and so on. So it's consistent with that. Okay. Now, you should have asked, I mean, one thing you could ask in the ADS-CFT is all this discussion that there is about alpha vacua, baby universes, and so on. I don't know if you have heard of that. But there are some cases in which all these alpha vacua, they seem to correspond to parameters also in the gravity side. And that would be against that would be against this conjecture of no global symmetries. And that's why there's a paper of Kunrum Baffa and Jake McNamara trying to argue that in higher dimensions, there shouldn't be all this story of baby universes and symbols of CFTs and so on should not apply in higher dimensions because we would go against global symmetries. There's something to discuss there. Okay. So let me go on and let me go to examples. Okay, so I'm going to discuss two examples, rank 1 and rank 2, meaning that the first one is the easy one. I think we'll go fast because we have already discussed many things. So in the sense that we just have some field strength as a current, and then I will consider the case in which we have a product of two field strengths. Now, this is why I told you I will do this in more detail. Like when we have, for example, a BF theory, right? In 4 dimensions, so we have a B field and a one-form gauge field, and they are coupled this way, we have these four symmetries. Like we have the two electric ones and the two magnetic ones. And the point is that this coupling is already breaking two of them. So the two form global symmetry and the one form global symmetry is broken, while the one form magnetic global symmetry and the zero form global symmetry is gauge, okay, because the currents are exact, okay, they appear on the right hand side of these conservation equations. Okay, so everything is broken or gauge. So you could ask now, okay, what happens if we add charge states? Now, if we add strings and electrons, this is fine because they are breaking some symmetries that were already broken. So, I mean, it's fine. We are just breaking everything twice. And in fact, if we have a complete spectrum, they are going to break it completely and not just to a discrete remnant. Now, the problem is that what happens when we add monopoles and instantons to the theory? Because monopoles and instantons are going to break this one form symmetry and this zero form symmetry that in principle they are gauge because of this BF coupling. And this is a problem because you cannot break a symmetry that is gauge. This is an inconsistency of the theory. So for example, you can see this, that, I mean, if you take the second derivative of the first equation, okay, in principle, this should be zero, right? The second derivative, exterior derivative is always zero. But if there are monopoles, this is going to be non-zero. And this inconsistency is reflecting the fact that you're trying to gauge a symmetry that is broken by the monopoles. So what is the resolution of the puzzle? Well, the resolution is that the monopoles cannot be introduced alone. So if we have monopoles in this theory, we also need to have strings in such a way that they are attached to the strings. Because if we do that, then, I mean, we're going to have an extra term on the equation of motion for the B field, okay? So in addition to the MF2, we are going to have the current associated to the strings. And then what happens is that the current, which is gauge, the symmetry that is gauge, is this linear combination of the two, while the independent parts, or if you wish, the other linear combination, is broken, okay? So this part is what we call solitonic charge, right? Like it's breaking the symmetry, it's just some field configuration. And this string is some localized charge. So this is a combination that is gauge, while the other combination is broken. And the fact that it's broken can be seen from the fact that we can transform one charge into the other. So that's why I said that breaking the symmetries with localized objects or with the BF couplings or Chern-Simons terms are actually correlated, because we should be able to transform one charge into the other, because otherwise there would be some additional Chern-Simons symmetry that remains exact. Okay, so in order to avoid all the symmetries, I mean, one linear combination is gauge and the other one has to be broken, meaning that there should be a way to transform one charge into the other. And the way to transform one charge into the other is to take the zero size limit of a flux tube and produce some localized string. Okay, is this clear? Okay, so this is something that we will see many times. So let me say again. So the idea is that it seems that sometimes we try to gauge a symmetry that is broken by adding the states, but then the resolution is that it's a linear combination, the one that is gauged, and then the other combination is the one that is broken. Now, let's try to do this with the rank 2 Chern global symmetries, okay? So for simplicity, let me just consider the case, which is more familiar, which is, for example, the trace of F square, no, of some gauge field. Now, this is going to give rise to a D-5 form global symmetry in general, and that's why in 4 dimensions, it gives rise to the -1 form symmetry that we were discussing, okay? Now, we have two options. We can break it or we can gauge it, no? Now, to break it, we need to introduce charge states, no? So one option, for example, is to add monopoles to the theory, because then the Bianchi identity, right, which is going to be different from 0, is going to imply that the conservation of the current is F with F, right? It's going to be different from 0, no? Because of the presence of monopoles. Now, if we don't have, like, for example, we have a non-abelian theory and the group is simply connected, so we don't have monopoles, we cannot play this trick. And the only way that we could think of to break the symmetry is actually to unhix the theory to a larger gauge group. Okay, so one example is that, for example, if we have SU5, right, and we break it to SU3, SU2 cross SU1, if you are in the infrared, you seem to have 3 different Chern-Weil symmetries, 3 different F squared, no, associated to the 3 factors. But I mean, one of them is broken by the monopoles, the U1, and the other 2, the associated to SU3 and SU2, actually can be transformed into each other if the theory comes from an SU5, because we can always, in the SU5, we can always transform the SU3 instanton into the SU2 instanton. And therefore, this transformation of one charge into the other is telling you that the Chern-Weil symmetry is broken, so there is only one left from the 3 that you had, which is consistent with the fact that originally in the SU5, you only had one Chern-Weil symmetry. Okay, so summing up, either you break it because you have monopoles or because your gauge group can be unhixed to some larger gauge group in the UV, and therefore you can transform some of the instantons into each other.
Can I ask a question here?
Yes.
So once you go up to the SU5, though, you're still left with an exact Chern-Weil symmetry, right?
Yes.
So can that then be removed, or?
Yeah, perfect. Okay. Yes, exactly. So this trick, it doesn't seem to help to get rid of all the Chern-Weil symmetries, right? Like there's one that remains. And this is something very important because that's, it seems that just by breaking things, we cannot get rid of everything, which means that we need to gauge the remaining one.
Oh, okay, thanks. Yeah,
so the solution is that when we have a trace of F squared, I mean, some non-abelian theory, it seems that, I mean, we cannot get rid of everything just by gauging, by breaking. So we need to couple, I mean, like this F squared needs to be coupled to some gauge field so that the remaining symmetries left is gauge. And if we are in 4 dimensions, this means that it needs to be coupled to an axion. So that's one of the first conclusions, one of the first results. I mean, as far as we can see, it seems that we need to have actions to get rid of all the Chern-Weil global symmetries because there is always one that remains that we need to gauge with the action if we are in 4 dimensions. Okay, very good. So the last thing about this example is that, okay, here is fine because I'm talking about a non-abelian theory, so I just couple to an axion and that's it. But imagine now that we can do both things. Like we can, like for example, we hix this theory to a U1. So we can either add monopoles or also couple to the axion, okay? Because that would be this case in which we seem to gauge and break at the same time, okay? Now, what happens in that case? So if we gauge it by coupling the F squared to an axion, but we also have monopoles, like for example, the Topf-Polyakov monopoles that comes from hixing SU2 to U1, then it seems that we again run into a contradiction as we had for the BF theory, because we are trying to gauge and break the same Chern-Weil symmetry, the F with F, at the same time, and that's not consistent, right? Like for example, if you study the equation of motion for the axion and take the stereo derivative, on one hand it should be 0, but because of the monopoles it's non-zero. So the resolution here, so let me tell you, in the BF theory, the resolution was that actually the current that was gauged was not just F with F, the Chern-Weil, but F with F plus something. So there was some linear combination that was gauged, and that was the resolution. Now you could ask here, what is this extra thing, right? I mean, how we solve this? Because there is no candidate for this extra term. And the point is that, well, this extra term has to satisfy that the stereo derivative takes this form so that we solve the puzzle. So it has to be something that is localized on the monopole. Okay. So the resolution is that in order to gauge consistently this Chern-Weil symmetry, if we have monopoles in our theory, these monopoles has to have world volume degrees of freedom. So in this case, for example, if we are in 4 dimensions, it's just a compact scalar that is localized on the monopole in such a way that, I mean, this would be the Lagrangian, the world volume Lagrangian for the monopole, in such a way that when we compute again our equation of motion for the action, there is this extra term proportional to this world volume degree of freedom that lives in the monopole that solves the story, and then this linear combination is gauged where the other one is broken and everything is consistent. So gauging the Chern-Weil global symmetries in the presence of charge states requires you to add world volume degrees of freedom in the charge states. This is the next conclusion. So actually, I mean, we derive this just by consistency of breaking these global symmetries, but this compact scalar is famously known to exist in the Topf-Polyakov monopole. Like if you study the zero modes of the monopole, you can see that there is this dionic field, which is precisely the one implementing the Witten effect. So that when we have the monopole and we shift the action, we also induce electric charge. And this effect is just a consequence of gauging in a consistent way the Chern-Weil symmetry. Okay, so this is the next conclusion, that consistent gauging of Chern-Weil global symmetries in the presence of monopoles imply the existence of localized degrees of freedom. So the existence of these degrees of freedom is known, and like you can compute it and find out they are there, but we can see that they are there for a fundamental reason, which is gauging these global symmetries. Okay, any question?
Yes, can I ask a question actually?
Yes.
So if you're happy to break the symmetry anyway, do you really need to gauge it? Like, what if you just give up on gauging and just break it, and then you don't have the symmetry anymore?
So if it's an abelian thing, it seems it can be fine. The point is that if it's non-abelian, as we said before, it seems that you cannot break everything. Like there is always one that remains.
Got it. That was okay. I see. I remember now. Yes.
Yeah. So that's why you need to gauge it. And then since you need to gauge it, you have to do it in a consistent way, and therefore you need to have the localized degrees.
Got it. Okay. Okay. I see. Thank you very much. Yes, indeed.
Yeah.
You said that before. Yes. Yes. Very good.
That's the.
And for 4 dimensions, the only extra CW global symmetry is this F wedge F. Is that correct? This current 4-form current. There's no other exotic current. Is that right? That you can F.
Well, actually, you can also consider like phi F.
Ah, phi F. That's right. Yeah, you had phi.
But it's already like, I mean, you can see that it's also broken, and it's fine. Like there is nothing special happening.
So nothing special happens with that. So this is really the only possibility, is this F wedge F. That's kind of interesting.
Yeah, I think it's the most interesting one. Yeah.
Mm-hmm.
Yes. Okay, so let me say a few words about the phenomenological implications. Now, as I said, just to repeat the message, but I mean, to make it clear, we know of no way to completely break all the Chern-Weil currents when we have a non-abelian gauge theory without coupling to some gauge field. And that's why this seems to imply the existence of actions in 4 dimensions. Now, this is nice because it can, I mean, it gives some reasoning, like some fundamental principle why we need to have the QCD action, right, to solve the strong CP problem. And you could also ask, well, whether this story is helping also with the action quality problem. No? So when we try to solve the strong CP problem, we can have a problem, I mean, we don't solve it, if the action, the QCD action, also couples to other things, right? Because that could spoil the resolution, because the minimum then could be at a different place that is not aligned with the QCD minimum. So, I mean, it could be a problem. It's something to take into account when you do Vision standard model. Now, what we can say about this is that if it couples to other things, okay, then only this combination is gauged, which means that the other combination should be broken. Well, actually, it can be 2 things. Either the other combinations are also gauged, but then you are going to have more actions. So in the end, there is no action quality problem. You can just diagonalize and have only one action for QCD, and that's it. But the other option is that the other combinations are are broken. But breaking means that you should be able to deform one charge into the other. So if the QCD action is coupling to other things, these other things should be connected somehow to QCD. And this might ameliorate the action quality problem, because there might be some correlation then between the different phases and so on. Now, we have not studied this in detail. This would be something interesting to study in the future, try to see how this correlation that is necessary in order to break all the Chern-Weil global symmetries affects in practice the potential for the QCD action, and whether it helps with the action quality problem or not. Any question?
But the S other here, this is from some other gauge group, other non-abelian gauge.
Yeah, so exactly. So it has to be something that is connected to the QCD action, in the sense that I can take the QCD charge, take it to the zero size limit, and produce some other instanton. The easy way to do that is that indeed is this QCD, like these instantons, come from unhiggsing, some larger gauge group,
right?
And that's how they are transformed to each other. But then you are going to have constraints, because our standard model comes from unhiggsing, some unification and so on.
Yeah, but you're saying that we could start with a SU5 theory with an axion, but then when it descends, there'll be some coupling between this axion with QCD and
SU2
and the SU2 part as well, right?
Yes.
That's what you're saying. Yeah.
Yes, exactly. That's what I'm saying. And I'm saying, it doesn't completely solve the problem, because it's coupling to other things, but I think it might ameliorate it, because those things should be related. So there could be correlations between the phases and so on. So you cannot just write whatever you wish on this right-hand side. You have to write something that is somehow connected.
Yeah, but I'm still confused about, because can't I just write down other terms that explicitly break the U1 Peccei-Quinn symmetry that have nothing to do with this coupling? And so it's not going to address those contributions.
If you do that, the problem is that you are going to have a Chern-Weil symmetry, which is going to be given by the other combination that I'm not writing here, like with the minus sign, right? Like that you are going to have the trace of F which F minus the other contribution. And that's a Chern-Weil symmetry that should be broken or gauged or something in quantum gravity.
Oh, so you're saying that when people just generically add higher dimension operators, which explicitly break the U1 Peccei-Quinn symmetry, you're saying that secretly there is also Chern-Weil global symmetries that need to be further broken?
Exactly.
Oh, okay. I see.
So, if you add more things, we are going, since only one combination is gauged, right? Like the combination that couples to the action, all the other combinations of these other things, they are also Chern-Weil symmetries that should be somehow broken. So you have to take care of that.
What does that mean? Adding more axions?
So either you add more axions, but then, it's like you don't have that, or you break it in the sense that there should be some continuous process, like some smooth deformation in your theory that allows you to transform this QCD charge into these other things, which is actually constraining what other things you can add, because you cannot transform QCD and everything you wish. Like, there are constraints there. But so breaking, it means that, like there is a smooth process that relates all these contributions.
I see.
So it's constraining more, than what we usually do.
Okay, yeah.
Well, just to follow up the discussion, my naive understanding is that you have to introduce an axion field to break the CW symmetry. So if I have if the same axion couples to other gauge field in this form, you okay, in other words, if I have other CW symmetries from other gauge fields, in principle, I need to introduce other axion to break them. However, if I don't want to do that, I want to like a one axion to break the CW symmetry for all the additional gauge group, but they have to be done in a correlated way. Is that why you are saying if it's broken, we have this logic, so, I have to perform it? But it does not tell me that yeah, I think I agree with you. It's in a correlated way, but it doesn't tell me the angle has to be aligned by these different contributions.
Yeah, I don't know exactly. So it's, I don't know, something to study. I don't know how this correlation that is necessary to break the Chern-Weil symmetry, how it translates in practice into the phases and so on. That would be something to study. Sorry, I think, like, for example, like if we think that this correlation comes because they come from a gut unification group, right? That's one possibility. I think the phases are correlated, right? I mean, I don't know how to write it in practice, but I mean, it's some computation that has to be done. Probably people have studied this. Actually, I'm not very sure about that. But like that's the more familiar example, right? Like let's imagine that this correlation comes because we are unhixing for another gut group. Then the phases that we will get for X potential are going to be correlated, and then it could ameliorate this problem. I think the same correlation that appears there is going to appear with any other term, because any other term that we add, since it has to be correlated, is like if it's coming from some unifying group in quantum gravity. Like there should be a way, when I say that there is a process that that transforms one charge into the other, it could be something more exotic that cannot be described in field theory. Maybe, I don't know, maybe it's not like some gut unification, but this transformation is also some sort of unification. Like there should be, from a UV perspective, there should be the same thing. And it's just that from the IR, they get split into the different contributions. But there should be a way to unify all of that into the same thing in the UV. And therefore, that's why I expect that the phases somehow should be correlated. But yeah, one should work to explicitly show what the correlation is and to work out the numbers. No?
Yeah, thank you.
Any other question? Okay, so I think I'm running out of time. Maybe, so this is just, I'm almost in the end. Probably what I can do is just, if you give me probably 2 minutes, I can go quickly through the string theory part and just give you the take-home message. And then
yeah, just go ahead. Yeah, just take a couple more minutes. It's fine. Yeah.
Okay. Yeah. So the thing is that, yeah, here we are forcing that the symmetry should be gauged or broken. But in all the examples that we check in string theory, like we have a large, like most of the paper is actually about checking example and making sure that this is correct. The symmetries are always gauged and broken. And not only that, one of the nice things is that we can rederive string theory and many aspects of string theory just from this. So one exercise that we did is, for example, to rederive type 2A string theory, like all the brain, the existence of brains, the fields living on the brains, how they connect to each other, and how many things, just from requiring the absence of these symmetries. Like one thing implies the other. So just to give you quickly what the story is about, like what we did, for example, to pick one example, is you can start with the type 2A supergravity that doesn't have brains or anything like that, or charge states. And you can study what are the possible Chern-Weil symmetries that you have in your theory, like all the products that you can have. Like here, there are many more options, right? Because we have higher force fields. And then you can see that they are all broken, except for the one corresponding to G0 and H3, which implies the existence of D brains and S5 brains. Let me skip this. So just by requiring that the symmetries are broken, then we need to add these brains. And once we add the branes, we run into the same puzzle that we had with the Topf-Polyakov monopole, in the sense that we are adding branes which are breaking some symmetries that were also gauged. So the branes cannot be alone. They need to have dynamical Warb-Wohlers degrees of freedom. And this is exactly the same than for the Topf-Polyakov. It's just changing the degree of the forms, okay? But this, I mean, I can go maybe quickly. The thing is that in this case, the problem comes from a 4-form gauge field, okay? When we add some D6 brane. And the thing is that we need to add something that modifies this equation of motion. That has to be something that is localized on the D6 brane, and it's a 2-form field, okay? So in this case, instead of having a compact scalar to solve the problem, what we need to have is some gauge field. So we need to have gauge fields living on the branes to gauge consistently all these Cherrbile symmetries. So just with this, we can derive the existence of gauge fields in the branes, which can actually be understood in general as Goldstone bosons from the spontaneously breaking symmetries. And well, this is something that it seems to be a matter like of the lamppost, and I mean we can show that is general just by consistency of the symmetries. So once we have the gauge fields living on the branes, using gauge invariance, we can rederive the brane action, the Chern-Simons action. And then this is going to imply the existence of the lower dimensional branes, because a higher dimensional branes induce lower charge. And this is the other process that we discussed, that when we have several contributions, since in this case the Ramon-Ramon fields are gauging some linear combinations, the other ones have to be broken. And this process of transforming one charge into the another in string theory is very well known, and is what give rise, well, is what allows you to generate lower dimensional branes from the higher dimensional ones. So once we have the D6 brane, for example, we are going to induce some D2, some D2 brane or D4 branes because of this Warp volume fluxes, and this is necessary in order to break all these other combinations. So the fact that we can take the zero size limit of some instantons and give rise to a lower dimensional brane, which is a very well-known process in string theory, is a consequence of breaking these other combinations and these other Cherrbile symmetries. So breaking the Cherrbile symmetry allows you to deform one charge into the another, and this is the discussion that we have for the actions in the QCD. Okay, it's just the same thing, but now in string theory. So one can go to further and then study higher ranks, not just F watch F, but like with like higher products. And all of them seem to be broken when we add branes, except for, I mean, some that get broken only. So in the moment in which we have branes, these are going to be breaking, but then we're going to have new currents that are proportional to the intersections of the branes. Okay, meaning that in order to fully break everything, we need not just fields living on the branes, but fields living on the intersection of branes, and so on and so forth. So there is like a sort of a Matryoshka-like structure, in the sense that if we consider Cherrbile symmetries of rank 1, so the usual P4 global symmetries, breaking the symmetries require the existence of charge states. If we have rank 2, breaking the symmetries in a consistent way seems to require localized fields living on the branes. And if we go to higher rank, breaking the symmetries in a consistent way require also localized fields living on the intersections of the branes, and so on and so forth. And this is all the structure that we observe always in string theory, which is, I find pretty amazing how we can rederive all these things just from requiring the absence of global symmetries. And this might hint also that all these complicated ingredients that we get from string theory, all these higher dimensional objects, and how they relate to each other, and how some of them end into each other, and so on, might be general features of quantum gravity if we believe that global symmetry should not be allowed in any consistent theory of quantum gravity. Okay, so this is it. So let me summarize. So yeah, we wanted to draw the attention to this large class of global symmetry. Sometimes, I mean, there are works that some study, maybe some of them, like the trace of F squared, there were some works in which they pointed out that it's also correlated to some global symmetry, but there was no systematic analysis of all the possibilities. So we decided to give it a name, like to have a unifying picture and explain in more general terms what are the ways in which these symmetries can be gauged or broken. And for example, the existence of axioms can be understood as a consequence of gauging the Chern-Weil symmetries, which seems to be necessary if we have non-abelian theories, because we couldn't find a way to fully break it completely without gauging. And also, if we gauge a Chern-Weil symmetry in the presence of Char states of monopoles, then we need to have word volumes localized degrees of freedom in these monopoles. And by playing this game, we can rederive many aspects of string theory. I did the example of type 2A, but you can do the same in heterotic string theory, M theory, in AdS/CFT, and rederive many aspects just from requiring the absence of this Chern-Weil global symmetry, which brings an interesting question, which is to what extent all these complicated ingredients are just a matter of string theory, or maybe more general than that. Okay, so let me thank you for your attention and ask if there is any further question.
Yes, thank you, Irene. Your virtual applause. It was a very interesting talk. If there are other questions, please feel free to mute.
Another question. So apologies if you've actually already explained it, I missed it somehow, but if we just stick to 4 dimensions, something like UCD, is there some bottom-up argument in semi-classical gravity, perhaps, that tells me that I shouldn't have -1 form symmetries? Like the reason I ask, just sorry to be clear, is that, you know, for normal symmetries, there are like black hole arguments, which are admittedly a little bit hand wavy, but are at least very plausible that there should be something wrong with global symmetries. But for -1 form symmetries, is there anything like that?
No, there is no argument based on black holes because exactly there are no propagating degrees of freedom. So that's missing. From the perspective of string theory, since by T-dualizing and things like that, you change the dimension of the objects, we tend to extrapolate what is known for 1 form to 0 form and then -1 form and so on. And so in that sense, it's more natural. But from a bottom-up perspective, there is no argument based on black holes whatsoever.
From the point of view of string theory, anyway, the world isn't really 4-dimensional, probably. So the thing that to us looks like a -1 form symmetry is secretly some more standard symmetry.
Well, yes, exactly. Like there are 2. So it's true that if you have extra dimensions, you can also think of these -1 form symmetries as ordinary symmetries in higher dimensions. So then it makes sense that something is wrong with them. Yeah, so yeah, exactly. So from string theory is fine. From a bottom-up 4-dimensional perspective, there is no argument yet. It's related to the absence of free parameters. So you would like maybe to require that in your your theory of everything, like in your UV completion of quantum gravity, that there are no free parameters. But that's more a wish than, yeah.
Yes. So can you actually elaborate on this connection between a -1 form symmetry and the absence of free parameters? I mean, can you, is that the statement?
Yes. So exactly. So the thing is that let's see. So a P4 global symmetry is associated to some P4 gauge field that has a P+1 field strength. So the current is a P+1. So if we are talking about -1 for symmetries,
the current
is a 0 form.
Yeah, the current is a scalar now, right? It's the Hodge dual of this 4-form current.
Exactly. So the current of a -1 for symmetry is a parameter because it's a 0 form, and it's the dual of a 4 form, right? Of like the field strength of a 3-4 gauge field in 4 dimensions. So that's why it's associated. So and now the fact, yeah. So the current is this parameter, And that's why if the current is not so there are two things now that you can do, break or gauge, right? Now, it seems that gauging makes complete sense actually, because it's completely fine to ask whether that current is exact or not, even if it's a top form. So it's a pity I cannot write. the current, okay, in the way I'm writing this, like the P4 global symmetry is associated to a D minus P minus 1 for current. So a -1 for symmetry is going to be the top form, like the field strength of the 3-4, the 4 form in 4 dimensions. So this is the current, it's a 4 form. And then to ask whether it's exact would be equivalent to ask whether the symmetry is gauge. And even if it's not, it doesn't have propagating degrees of freedom, it makes sense to ask whether a 4 form current is exact or not, like whether you can write it as D of a 3 form or not. If it's exact, means that it's gauge, and that's what gives rise to the axion monodromy and all these things. Now, the breaking is more exotic, because breaking is that the conservation of the current is non-zero. So it's that the exterior derivative of the 4 form has to be different from 0. And this seems tautological because in 4 dimensions, this is the top form, right? Any derivative you take seems to be 0. So how come this is non-zero? How come you can break -1 for symmetry?
Exactly. Yeah.
That's the exotic part about -1 for symmetries. Okay, it's not about the gauging, it's about the breaking. Now we believe and we give arguments in the paper of why we think this still makes sense, but you have to think of it instead of taking the derivative in space-time, you have to think of it in configuration space. So it's like the question of whether it's broken or not is about whether there is some process in the space of field configurations that allows you to change the value of the 4 form. Like whether there is some smooth deformation in your space of field configurations. If there is such a deformation, then the symmetry is broken. And that happens, for example, when we have some dipole constraint. Like for example, when we have some additional constraint that fixes the parameter to some value, you can bring back this with a Lagrange multiplier to your Lagrangian. And if you study the equation of motion, you will see that then this Lagrange multiplier is like a 4 form field, gauge field. So I mean, it doesn't have propagating degrees of freedom or anything. But then if you write the equation of motion, it seems that the dF4 is going to be proportional to the field strength of this Lagrange multiplier, and then it should be non-zero. So in string theory, I mean, whenever, I don't know, we have like dipole conditions, like there are some parameters that are fixed. From the 4-dimensional perspective, they can be seen as these Lagrange multipliers, and that would be equivalent to break these global symmetries. I know it's especially because I'm not writing, so maybe it's difficult to keep track of it. But
yeah, but probably I think what you said before to Alexi, probably the fact that it's descending from higher dimensions, that's probably the origin of it, right?
Yeah, in higher dimensions is transparent and and clean and easy, because in higher dimensions then it's not a -1 for symmetry anymore. It's a higher 4 symmetry. And then everything makes sense. Like these 4 forms, I mean, make sense in higher dimensions, and you can see that it's gauge or broken and so on.
So then maybe your conclusion is that not only do you predict that we have axions, but also that we live in higher dimensions too.
Yeah, well, yeah, I don't know. Yeah, if it would be easier, yeah, if we live in higher dimensions, because then the interpretation is much easier. I think it could still make sense in lower dimensions. I mean, we're trying to also formalize this. Like, I don't know if you have heard, there is also this modern approach of talking about global symmetries in terms of cobordism. There is like a new mathematical framework to discuss all these things that could actually also talk about -1 for symmetries, and it's mathematically correct and it's fine. So I think there might be a way. I mean, now it seems exotic. I think probably in a few years it will be more transparent and clear. At the moment, I completely agree that it makes sense when we have extra dimensions, and otherwise it seems very exotic and weird. But there are some cases like the axion monodromy, when we have the axion that receives some flux potential, some scalar potential, and we have this multi-branch structure that we use in inflation many times. This type of process that maybe people are more used to, I think it's just a consequence of gauging this -1 for symmetry. It's just like the Stuckelberg coupling, but with an axion eating some parameter, and that's why it gets some mass. So I think there are still there are some processes that we are used to them, and we can reformulate it using this language, even if it seems exotic. Hopefully in the future we'll have a better understanding of what it is. But yeah, at the moment, I agree. I mean, you can think it makes sense if you come from a string theory and you have extra dimensions.
I see.
I have a question about your slide on the rank 2 Chern-Weil global symmetries.
Mm-hmm.
So if we just consider four space-time dimensions. I'm not sure if it was a slide, but anyway, yeah. If we have
or gauge it.
Gauge it. So we have an axion coupled to trace F wedge F.
Mm-hmm. So
yeah, and here, so then we get a two-form U1 symmetry, the sort of axion string symmetry, right? Mm-hmm. But because the axion's not coupled to it's not coupled to D of a 3 form, it's F wedge F. I don't think that symmetry is gauged, right?
Yeah, that's a good question. Yeah.
Okay, so do we then have to gauge that symmetry as well by introducing other couplings, or it can't be broken, right?
Exactly, it can be broken. Yeah, exactly. That's something I was thinking a lot, actually. There seems to be a fundamental difference. If we have a trace of F wedge F, or we have directly some F4.
Right.
Because in the latter case, we are gauging the two-form global symmetry of the B field, while in the former case, it is not gauged. The point with that one is that, there are two things. First, it's a tricky symmetry in this case because actually it's not gauge invariant. There are no charge operators which are gauge invariant under the symmetry. So if you write it's a two-form global symmetry, so you should have some one-form operator, right? Like living on a one-dimensional manifold, like some string.
Just axion string. Axion strings are possible. What's wrong with them?
Yeah, can't you write a sort of defect operator that it's like the world line of the axion string, right? But you're saying it's...
But I think it's not invariant under the electric symmetry, right? We have this Witten effect. Yeah, I can check.
Yeah,
but
I would have to think about that.
It's a tricky one. So let me say. So it's there. I agree, but it's not what we call a genuine operator in the sense that it's completely gauge invariant. So I'm not sure if it really counts as a global symmetry or not. But in any case, even if it takes the perspective that it counts, if we add strings, then we are breaking it, and then it's fine. Like there is nothing happening.
Okay,
so, but I'm saying this because I'm actually thinking of that example, and I haven't made my mind yet of whether it should count because of this gauge invariant issue.
Okay, thanks.
Something to study in more detail. But in any case, even if it counts, yeah, then you would need to add strings to break it. And these strings automatically, they should be able, actually they can break because of the presence of the monopoles.
You could gauge it too.
Yeah, I'm
right,
not sure
if you gauge it, then then you're really secretly gauging a different linear combination of the Chern-Weil symmetries, I think, right?
Exactly.
So,
Exactly. Like if you gauge it, it's like you are adding an extra 3-4 gauge field to gauge it. And then you gauge a linear combination, but then the other one should be broken. So, I mean, you are not winning anything. Like we still need to break this one.
Interesting.
But yeah, there is also, and I'm also thinking about this because there is this question, like it seems that with a non-abelian theory in the low energy limit, like you can think of the trace f squared as some f4, like you can think of as the Chern-Simon gauge field, and then you have like the typical, also like this axiom monodromy thing that it seems you are gauging, and it's also what Gia Bali uses in his papers, that he claims is like a 4-form and so on.
Exactly. Actually, I was going to mention that before, that Gia Dvali has been for many years promoting the idea that you should be thinking of the axion physics as this 4-form.
Exactly. Yeah. So in order to think about this, the QCD as the 4-form version, we should be able to gauge this 2-form global symmetry. And as I said, I'm not, it's very, very tricky. So I'm thinking of that because I use this Gia Bali story many times, or so like I did many models of axion monodromy and things like that. And I thought it was sort of natural, and at some point I believe in that. And now I have my doubts, and I think there is a lot of subtleties here and a lot of interesting physics to uncover that I hope to have a new insight now using this Chern symmetry. So that's why I said it's not gauge invariant. So there seems to be a difference, and maybe the point is that in the infrared there is like some sort of emergent symmetry, and you can still make sense of it in an approximate way. But there is some fundamental difference with the F4. It's not exactly the same. And it's something, like I would like to understand it better in the future, how to make sense of that. I mean, I want to take the Bali story and make sense of that, like using all this language.
Yeah, that was always the problem, I think, is that it was a bit opaque, his story. And the axion, I mean, in terms of doing phenomenology, just doing it with the axion is much more straightforward than doing it with this 4-form. But he was always arguing that that's the way you should think about it, and you can understand everything that way. But
exactly.
But maybe you're saying that this approach is the way to understand it, but there could be it could be subtleties in trying to get it to work, I guess. Is that what you're saying?
There are subtleties, as I said, like because with the 4-form we only have the gauge invariance of the 3-form, but here we also have the gauge invariance of the 1-form gauge field.
Yeah.
And I think this implies that these operators under the 2-form gauge field are not gauge invariant under this 1-form gauge field, and one has to be careful. How to do it.
But can you think? Are there any other pheno applications that you can think of in 4D, or is it mostly just related to axion physics?
That's a good question. I mean, it's true that so far I only thought of axion physics, like both with the QCD or the axion monodromy or the Bali story and so on. The problem in 4 dimensions is that we don't have so many higher forms. So it's
exactly.
I
mean, it's still interesting for the axion, but I was just wondering, if you had thought of any other possible applications.
I haven't thought of that, which doesn't mean that they are known. I mean,
there
could be others. I was just thinking of the actions, but it would be interesting to understand more. Maybe with these word volume degrees of freedom, I don't know, like it's normal for the Topf-Polyakov monopole, but maybe it has other applications in other cases. I don't know, maybe there are models that do not have these word volume degrees of freedom, and then they should be problematic. But yeah, I would need to think.
Well, like, I mean, for instance, for cosmology, people talk about axion strings, right, in the early universe. I mean, are there modes on this axion string that people haven't included before? Is that a possibility?
Yeah, exactly. So one should be careful about what strings, because the strings, either they have more degrees of freedom, or they should be able to break, or like there are some constraints that they need to satisfy. So if you have just some cosmic string charge under some global symmetry, that would be inconsistent with quantum gravity in principle.
So maybe then there, I see. So
Oh.
maybe then there are applications, say, in more in the cosmological setting with cosmic strings, for instance.
Yes, could be.
Mhm.
Yeah.
I have to run away to teach, but I wanted to say I really enjoyed the talk. This was great. I wish it was in person so we could go to the board and discuss it.
Yeah, thank you.
It was really very interesting. So,
Thank you for the invitation.
so I have to step away. Doesn't mean anybody else has to. But yeah, bye bye.
Okay, bye.
I'm also stopping the recording.